Can everyone attending remotely see my screen? You're going to have to speak actually, because now I can't see the chat.
Yeah.
Okay, good. Thank you. Where are we at? Right, okay. So we was at the polydispersity index, and we was measuring the heterogeneity of polymer samples there. So as I say, what we're moving towards now is understanding how we can get these polymers into solutions in order to do the measurements, which we'll introduce in module 4, lecture 4, whatever you want to call it. I actually normally call them modules because we're not moving by set lectures as such. They're just slide decks, if you like. So we stopped when we got to the point about critical molecular weight in there. So we already know now that these polymers are long, they're randomly called interpenetrating chains, but at a sufficient molecular weight, they can occur chain entanglements, and that causes a restriction in flow or movement. So if polymer chains just simply touch each other, it can result in an increase in viscosity, but it's not dramatic. Now, one example I like to use to talk about critical molecular weight is to talk about different stiffnesses of cables and rope, and also the different lengths and how that has an effect on the entanglement which they could face. So let me just put a new slide in here. Oh, that's not the right one. There is a right one here. Okay. So this analogy actually is taken from a guy called Stephen Abbott, who has a website all about polymers. So it's an excellent resource. Let me write his name down. This is an excellent resource if you want to see how some of the polymer properties change. He explains them in very nice terminology. So his example is that when we're talking about entanglement, if we take a stiff rope, we take a laptop cable, and we take a headphone cable, we know that as we move from stiff rope to the headphone cable, that the thickness would decrease. Okay, so the stiff rope is relatively thick, and the headphone cable will be relatively thin. Now, everyone knows if you jumble these things up, the stiff rope will remain stiff. It'll be easy to separate back out again. So if you pull it apart, it will separate very easily. The laptop cable will get into a tangle, but it'll be difficult to pull apart at first, but you can manage it. Now, everyone has had headphone cables in the bag or whatever, so you know that when those things get tangled up, it's very difficult to pull those things apart. And actually, often when you start to pull those things apart, it actually makes the entanglements worse, right? So you're actually pulling them, and it's actually causing more knots to occur. So if we increase any of these, so we take the stiff rope, the laptop cable, or the headphone, and we increase the length of any of them, what happens to the tangling? Does anyone know? So if we take a stiff rope and we increase the length of it, what will happen to the tangling of that rope?
It would increase.
Yeah, so it'll become easier, right? And that stands true for polymers as well. So if we make polymers longer, the number of entanglements that can occur is more, right? So if a chain is short and stiff, it's very easy for the polymer chains to be pulled apart in a solution or a melt. And if the chains are long and thin, untangling the chains is difficult, and that results in high viscosity and adhesion of the chains. Now, the definition of entanglement is really straightforward. So if we take an arbitrary plane, entanglement is described as, let me just change the color of this so you can see my polymer. Entanglement is described as when a polymer chain crosses an arbitrary plane more than 3 times. That now is an entangled polymer. You can imagine that that's not a chain existing on its own, right? There's lots of other polymers in the immediate vicinity. So the idea is that if it only crossed twice, let me go back to my color of my plane. So if it only crossed this plane twice, we can actually add force to the middle bit and that should pull clean pretty easily. Now, once it's entangled 3 times, that doesn't become as easy to do. So that's why it has to cross that plane 3 times in order to become entangled. Because actually what happens is you start pulling that chain that's crossed over the plane 3 times, you'll start to trap other chains in there. And that's kind of what happens with your headphones in a way, right? You start pulling on one bit, another length of the cable gets trapped. So that's how it explains the entanglement in there. But as a result of the entanglement, different polymers have different critical molecular weights. Ooh, a lot of color changes, yeah. And we just call that MC, so that's critical. So polymers such as polymethyl methacrylate, polyvinyl acetate, and polystyrene have a high critical molecular weight. Now, examples such as polycarbonate exhibits extensive entanglement even at modest molecular weight. Therefore, it's exceptionally tough, and you'll hear of polycarbonate being used as bulletproof screens and things like that. So that's why it's pretty strong. So that's an explanation of that entanglement and the critical molecular weight. So the critical molecular weight is that molecular weight in which these stable entanglements will occur. So that's in the notes there. Now, the important aspect, as we said right at the start, is that when we want to make a measurement of a polymer, we've first got to get the polymer into solution. So we've got to find the right solvent in order to dissolve our polymer. Now, all the methods that we'll come across, I think, yeah, we do need to dissolve the polymer first. So if we want to measure the molecular weight of those, whether we're doing viscosity measurements or we're doing ultracentrifugation measurements, we need to get it dissolved first. Now, to understand the polymer molecular weight measurements, we need to first understand the solubility, and we also need to understand the polymer solvent interactions there. Now, the key thing to dissolving anything is that like dissolves like. And that's kind of chemistry 101, right? So if you have polar molecules, you need a polar solvent in order to dissolve it. If you have non-polar molecules, you need a non-polar solvent to dissolve it. So in the first instance, when we put a polymer with a solvent, the solvent diffuses through the polymer mass. So that's the first instance of the polymer becoming kind of solvated there, right? We're trying to get the solvent to integrate into the polymer. And then what we get as a result of that is 2 different options. We either get a solvent swollen mass, Now you'll know, right, and you'll remember from before, from right at the start, in order to get a swollen mass, we need to have crosslinks in there, right? So this is kind of thermoset territory. And then we also, we can also get what is just a generally solvated mass. So that's where the solvent is fully integrated around the polymer. Now, depending on the polymer and the solvent that you use, you can get two different types of interactions. The first interaction is when the polymer-polymer interactions dominate. And in that scenario, we aren't getting a solvated mass, so it doesn't dissolve, because the polymer is more attracted to itself than it is to the solvent. And there's a few ways, there's a few things that happen here. You can get cross-linking. You can have a highly crystalline morphology. So these are the reasons why it might not dissolve. And then you might have strong intermolecular forces between chains. And what is the strongest intermolecular force?
Hydrogen bonding.
Yes, correct. So if we have hydrogen bonding in there, they're particularly strong. But then on the other side, we have an instance where the polymer-solvent interactions dominate. And in that case, we are getting the polymer solvated, so the polymer will dissolve. And in this case, what happens is that the mass will break up. So the mass breaks up, the chains disperse into the solvent, and that forms a solution. So one thing is to be aware of is that they use different terminologies. Obviously, solution is different to solute, and that comes in important when we talk about some of the measurements that we're using. So make sure you're aware of what the differences of those things are. Okay, so it's fairly simple, right? If we've got a polar polymer, we're going to put it in a polar solvent in order to solvate it so we can make a measurement. If it's non-polar, then we need to put it in a non-polar solvent in order to solvate it. Now, if it's somewhere in between, what we then need to do is kind of work out the enthalpy of mixing, and which we'll go into before. Now, before we go on to the next stage, I would say traditionally in the lab, you don't do all these calculations that we're going to go on to doing. A lot of people, when they want to find out the solubility of something, they will check all the solvents that they've got in the lab and make up kind of a solubility range there, and they will put a small amount of their polymer in and see if it dissolves, right? So not everyone will go through these steps of calculations that we're going to go through. But this is to give you some context of what's going on. So what we want to know is, what solvent are we going to choose? And to choose a solvent, the solution processes are governed by the free energy equation. That's the Gibbs free energy equation. I'm sure you've all seen this before. Oh, That's minus T delta S. So delta G is a change in free energy. And that must be negative for dissolution to occur. T, simplest one is temperature. Delta S is the change in entropy. And that's almost always positive. And it's always positive due to the conformational mobility of the chains. Delta H is a change in entropy, enthalpy. And if that's positive, we know it's an endothermic reaction. And if it's negative, we know that's exothermic. Now, the important thing for this is that the change in enthalpy determines the size, the sign of the free energy. And delta H must be small for dissolution to occur. So if it's a positive delta H, the polymer and solvent don't want to mix. But if the delta H is less than T delta S, the polymer will be soluble. If we have a negative delta H, the solution state is lower in energy versus the pure polymer, and the pure solvent state, therefore the polymer is soluble. Now, when we're talking about dissolving the polymers, we have a two-component system or a binary system there. And the two components in this are the solvent and the polymer. So in this heat of mixing reaction, we're attempting to define what is most commonly referred to as a Hilbrand solubility parameter. Now that parameter describes the degree of interaction between the materials and indicates the likelihood of solubility. So what we're trying to work out here is whether we can get our solvent integrated with the structure of the polymer in order to make it soluble in there. So I've written all this out. I used to define all this, but the equation for the delta H of mixing is on the left-hand side there, and all the definitions of the terms. But the important term with this is the cohesive energy densities, which are in here. And we've got V1 and V2 because they refer to the two different components. So one is the polymer and two is the solvent itself. So both the polymer and the solvent have cohesive energy densities. And that's why this equation is considered a binary two-component equation. So the cohesive energy density is the amount of energy needed to completely remove molecules from the neighbors, causing separation. So what we're trying to establish is the amount of energy it takes for me to move the polymers away from each other to get my solvent in. That's in the simplest terms. Obviously, there's a lot of depth to these equations, but that's what I'm trying to measure in this state. Now we can redefine this using the cohesive energy densities, or the square root of the cohesive energy densities, to give us the solubility parameter. And that's what we're interested in. So the solubility parameter can be rewritten into the equation, the two component equation at the top. But for delta H to be small, and for a negative delta G and dissolution to occur, the delta 1 minus the delta 2 in this must be small. And as a general rule, delta 1 minus delta 2 must be less than 4 in order for solubility to occur. Now, that's important because there will be a few questions which will tell you the solubility parameter for the polymer, and they'll tell you the solubility parameter for the solvent. You've basically got to work out whether it's more or less than 4. Okay? That's how simple we're going to do it. We're not going to go through all the equations. You don't have to do all this. It's just this time I need you to understand the context of what's going on here. Okay. So to determine the solubility parameter of the solvent, we use the cohesive energy delta E1 over V1. And that's the energy required to transform a given quantity of a substance into a gas. So that's what we're doing for this solvent. Now, similar to the heat of vaporization per volume for a volatile compound, and for a solvent, the delta 1 can be calculated directly from the heat of vaporization, which is this equation underneath here. So this is this heat of vaporization, or this equation here that we've got underneath for the solubility parameter version, is what we then call the Hilbrand solubility equation. So I'm not going to read all those different terms out there because they're defined in there. So the Hilbrand solubility parameter is essentially the square root of the cohesive energy densities. And to put it simply, in order to dissolve a compound or a polymer, and there are a number of interactions that need to be overcome. And the cohesive energy densities represent these energies for the polymer and the solvent. So exactly what I said before, the cohesive energy densities are these densities, the energy to pull one molecule away from another. Now, determining the solubility parameter of a polymer is a little bit difficult. So to determine, so polymers themselves have a negligible vapor pressure, meaning that they degrade before vaporizing into a gas. The vapor pressure is essentially a measure of a solid or liquid's tendency for particles to enter a gas phase. Now, to derive those, to derive the solubility parameter, we must use group molar attraction constants. So that's G or E to determine the delta 2. And these are derived from studies of low molecular weight compounds. So they're not going to study the polymer to derive these values. They're actually looking at these low molecular weight compounds, which will probably be the monomers to establish these values first. And they provide these numerical values for various molecular groups based on considerations of the intermolecular forces they'll experience between them. So the equation for this is that delta 2 is the change in the sum of G, which are these molar attraction, the density times by the sum of the group molar attraction constants divided by the molecular weight of the monomeric unit. So here is an example here for determining the solubility parameter for polymethylstyrene. So there is 2 different handouts there which you can get. These are actually the date seen here. These are the delta 1 values that we talked about for the solvent. So the example is to determine the solubility parameter for polyalpha methyl styrene, which has a density of 1.01 grams per milliliter. Use the solubility parameters and molar attraction constants from table 2 to 2.1 from polymer chemistry and 5.3 of the handout. Now I've done that for you. So I wasn't going to ask you to do that because I think you just need to see what's going on. But in order to do that, what we do is we use the values which are in this column here, and we work out how many different types of bonds or different groups are in there. We add them all together, and then we divide it by the numbers of those different groups in there. So 12 is a carbon, 10 is, sorry, this one's a carbon. This one here is a hydrogen. Now you put all that through the equation, and actually what you get out is this delta 2 value of 8.3. And then what we can do is we can go back to this chart here, this table here, which is table 2.1, I believe, and we can find out which solvents it would be soluble in. So using that Hilbrand solubility parameters, we could determine it would dissolve in pentane, hexane, diethyl ether, or ethyl acetate. And you can see that the difference between S1 and S2 is less than 4. That's the main bit, right? So you can see for all of those different S1 values for pentane, hexane, there is less than a difference of 4 between that and the solubility parameter for the polymer. Less than 4. If you remember that, we're good. So this was a think, pair, share, but I've kind of took a few of these out just because it's harder to interact in this environment with it. So one experimental method of determining solubility parameters means that you can take lightly cross-linked network samples of polymers in question and immerse them in different solvents whose solubility parameters are known. Now, I explain the rationale behind this. Now, if we take a cross-linked polymer, we know that it will swell in solvent. The better the solvent, the greater the swelling. Thus, the solubility parameter of the polymer may be taken to be the same as that as a solvent that causes a maximum swelling. So if we've lightly cross-linked our polymer and we're testing it in different solvents, the solvent which causes the maximum amount of swelling would be the best solvent for dissolving that polymer if it was not cross-linked, okay? So these are the general rules for solubility down here. So you can see that the general rules are that they like dissolves like, that polar solvents dissolve polar polymers. So that's if they have a permanent dipole due to charge separation. Non-polar solvents dissolve non-polar polymers, so there's no permanent dipole change in those, so that would be hydrocarbons and things like that. In a given solvent at a particular temperature, solubility of a polymer will decrease with increased molecular weight, and that's because we've got lots of interactions coming on, so we have to break those up even further. Higher temperatures generally increase solubility. There are some exceptions which we'll come to later on with polymers that exhibit lower critical solution temperatures, and they're important when we talk about thermoresponsive polymers a bit later, so we can modulate that response in order to kind of deliver drugs or expand and contract. We can do some cool things for those. Crystallinity decreases solubility. If we've got lots of crystalline structures, lots of those lamellae, plate-like structures in our polymer, then it's harder for the solvent to integrate in those and break up some of that, maybe hydrogen bonding or the intermolecular forces which are occurring. And then cross-linking eliminates solubility. And we should know that by now. I think you've been tested about 2 or 3 times on that one. So if you've got cross-links in there, your polymer will swell, but it won't become completely soluble. All right, hang on 1 second. I'm missing something on here. just switch back to. Okay, so I've drawn these ones in already. I knew I'd missed something off. Okay, so now the behavior of the polymer in the solvent is critical for different molecular weight measurement techniques. And in the ideal situation, we want the polymer to be completely solvated in there. So in an ideal mixture, if we have our solute and our solvent, what we want to do is get kind of a monodispersed arrangement of those particles in there. So this would be monodispersed. Now, once polymerization's occurred, that's a little bit different, right? Because you've got lots of monomers bound together to form a polymer. So we've actually got these chains which are dispersed into solution. Now, in a good solvent, those chains are expanded. So in a good solvent, we would say these are expanded chains. In a theta solvent, which we'll come back to later, the chains are neither expanded or contracted. They're actually in what they call a theta state. And we'll come back to that a little bit later on. Now, in a poor solvent, because the polymer interactions dominate over the polymer solvent interactions, what you actually get is a balling up of those polymers in there. So they actually contract, right? They really want to get close together. So in a poor solvent conformation, when they're in that balled up state, the delta 1 minus delta 2 is greater than 4. So we know that we've got a poor solvent in that system. This actually occurs more at lower temperatures because there's not as much energy in that system to separate the chains out, right? If we add more energy to it, we're going to get breaking up those chains a little bit more easier. And in that case, as I said before, the polymer-polymer interactions dominate. Now, in a good solvent, the conformation is expanded. So the chains are open, and they're freely moving around, they're freely solvated. In that case, the delta 1 minus delta 2 is less than 4. So that is a good solvent. And that generally occurs at higher temperatures, right? So as we get in more heat into that, we can intercalate the solvated molecules solvent molecules into the polymer to open that up. And in that case, the polymer-solvent interactions dominate in that sense. So what we're now thinking about is, once we've made our choice of the solvent, what is the polymer going to look like in that solvent? And in a good solvent, it's going to be expanded and it will allow us to make some really nice measurements or molecular weight measurements using whatever technique we choose. However, if it's in a balled up state, if we've chosen a poor solvent, the molecular weight measurements are not going to be true, right? There's going to be a slight offset into what we're measuring for those. So they're not going to be accurate. Now, what we can consider for this is when we're trying to measure whether it's balled up or whether it's expanded, is we can consider the hydrodynamic volume. And that's the average statistical volume or size of a polymer contained within solution. And that's dependent on the solvent interactions, right? And it's also dependent to a certain degree on whether we have branching and flexibility, molecular weight, intermolecular interactions. We'll kind of come to that in lecture 5. But there's lots of considerations there. What we can measure from that is kind of 2 measurements. We can measure what is called this end-to-end distance, which is around here, which if we take the ends of the polymers, we're measuring the distance between those, whether it's increased or decreased. So you'll already know, because this is fairly straightforward now, if we expand that polymer, that R value is going to increase. If we contract that polymer, then the R value is going to decrease. And that is dependent on whether it's in a good solvent or a bad solvent. And the same for the radius of gyration, right? We're measuring the movement around the center of gravity, if you like, in a and that's the S value. In a contracted state, that S value is going to be lower. In a expanded state, that's going to be higher. So the average shape of a cold chain is spherical, and in increased affinity, if there's increased affinity for the solvent between the solvent and the polymer, you'll have a large sphere and you have a large hydrodynamic volume in there. So there is a few things. So I've already written this in, but I'll give you some time to write this down. But there are a few things we can use to express that. So the average statistical size of a polymer in solution, we know, is dependent on the solvent interactions. The R squared value in there is the mean square average distance between the chain ends. So that was R from the other. S2 is the mean square average radius of gyration about a center of gravity. And SO2 and RO2 are the unperturbed dimensions. So that's the origin. So where did those things originate? And this alpha value is the expansion factor. And that's the one that we're really interested in trying to calculate and understand. This alpha value here. So for linear polymers, the R squared value, or the mean square average distance, is equal to 6 times the mean square average radius of gyration. So there's a few equations under there for the R2 and S2 calculations, but the expansion factor on this right-hand side is R2 over RO to the square root. Actually, you don't need the square root, so it's really just simply the R2 over the RO. Makes sense. Now, when we have a good solvent, this alpha value is greater than 1. And in that case, we have this expanded coil. So when the alpha value, and this is important, when the alpha value is greater than 1, we have a good solvent in there, and we have an expanded coil. In the theta state, or the theta solvent in this case, the alpha value is equal to 1. So that's an unperturbed coil. So that means that the mean square average distance between the chain ends is no different from the unperturbed dimensions in there. They're equal to 1. Then actually, I had to get rid of this. That's why I brought this one up. So if the alpha is less than, let me redraw that so it makes sense. That's less than 1. We know we have a bad solvent and we will have a tight coil. And in that case, the R2 value will be less than the RO value. So you have a bad solvent and a tight coil in there. We'll give you a couple of minutes so just to write the rest of the things down.
Dr. Mabit, under where it says for linear polymers, are those exponents?
Yeah, so that's the measure. Yeah, the measure for the chain ends and the expansion factor.
So when it says the R bar sub 2, is that R squared?
I don't think it is. No, I don't think it is in this case. Oh yeah, sorry. Yes, sorry, it is. Yes, it is a squared. Sorry. Yes.
Thank you.
Yes, it is a squared value. I will tell you again, in the exams, I actually don't ask for these equations, but you do need to know the alpha values for these things. So. A couple more seconds now. Okay. Now the expansion factor, or alpha as we determined there, is temperature dependent. And the theta temperature, when we're talking about theta states, you'll see this come up a few times. At the theta temperature, that's the lowest temperature at which the alpha value equals 1. So when we're saying that the alpha value equals 1, we're saying that the original state is no different from the kind of solvated state, right? We're not having any expansion or contraction in there. So the alpha value is equal to 1. So for a polymer for infinite molecular weight, the temperature at which the polymer exists as an unperturbed random coil is essentially the definition for that. Now the theta state was something established by Paul Fleury. So that's why it's called the Fleury conditions. A polymer of theta temperature and a theta solvent, the polymer is on the brink of insolubility and solubility, right? So it's right in between those things. The solvent polymer interactions are minimal, and just below this state, the polymer interactions will dominate, and you'll see precipitation, right? So you can't get that polymer to go into solution anymore, so it will start to precipitate out. Now, the diameter of the polymer chain random coil in solution equals the diameter of the amorphous bulk material polymer at the same temperature. Polymer molecules unperturbed by solvent but separated from each other, so they're not entangled in that state. So for any given polymer, the theta state can be achieved by doing two things. You can have a fixed temperature and you can adjust the solvent, and that would give us the theta solvent state. And then we can have a fixed solvent, but we can adjust the temperature, and that will give us the theta temperature in there. So just as a summary, you can recall that delta G equals delta H minus T delta S, which is a free energy of solution. When delta G is less than 0, we get the polymer dissolving. So when delta H is less than T delta S, the polymer will be soluble. For a theta state, the delta G equals 0. So the delta H equals T delta S for a polymer in the Fleury condition or the theta state. So if it's in that state, the delta G is going to be equal to 0. And from the theta state, it depends on the temperature and the entropy. So the entropy is most influenced by the polymer-solvent interaction. So if you measure entropy, right, it's the ability to kind of expand. So that will be influenced by these interactions which occur between the polymers. Now, all these parameters, in order to make a measurement of a polymer, we must use dilute solutions. So they all must relate to this dilute solution viscosity, which can then be related to polymer molecular weight when we actually show you how to do the measurements in the next lecture. So there's a YouTube video that describes that, and I've actually also put the link underneath there for Stephen Albert's page, and it talks a little bit about these solubility parameters in solution. Okay, so I think we've only got 5 minutes left, so we can stop it there, and then the next lecture will go on to making those measurements. I believe that should only take us one lecture to get through that, and then we're on to lecture 5, which is talking about all the different interactions that can occur to affect the physical and mechanical properties of these polymers. So we're slowly getting in towards the applications of these things. Okay, good. So you may leave, stay safe. If you have any questions, I'll be around for a little bit longer.
I had a question, Dr. Mabbott. Yeah. On lecture 2, there was a slide that you skipped and you said you would come back to that. It was about the general trends.
Yes, actually, good point. I thought of this morning when I woke up. I never came back to that, did I? Right, I'll fill that one in. No worries, I'll do that next lecture.
All right, thank you.
I did remember that this morning. I was like, I actually never went back and filled that in. Thank you.
Professor Mabbott,
Yes.
I actually had a question on the homework.
Okay.
So when we're doing when we're showing the polymerization of the monomers like on the A through M,
Yeah.
I was a little stuck on I and J, and I'm not really sure
Just 1 second. Let me have a look at the. Okay. So what is the issue with I and J?
I'm not sure if it should be like an addition or condensation.
Oh, okay. So you have. So describe to me which one you think it's most likely to be.
Okay, well for I was thinking that it should be an addition because of the double bond at the very top of the monomer.
Sorry. Yeah, that makes sense to me. Sorry.
And then for J, when we're adding those two monomers together, do they get added by their two double bonds at the top?
What do you think? So, okay, let's put it simply. If you have a look through some of the tables, have you seen that double bond O CH3? Have you seen that react with anything in order to form a condensation reaction?
No.
Okay. So you're right. Has to react through those double bonds at the top end, right? Because actually that group underneath there is an acetate group, I think, right? So it's not going to react through that.
Okay.
The main ones is that if you're looking for the condensation reactions, you're looking for the functional groups. So you're looking for the carboxylic acids, the alcohols, the amines, some others in there. It's very early in the morning for me, but there's some others in there that you'll also have to look for. If you find those, then there's a good chance that it's going to react by a condensation reaction. But remember that it's got to react with the other functional group in order to form a linkage. So the one that I always give is that carboxylic acids have to react with an alcohol in order to form a polyester. In those cases, those groups do look functional, and actually I think the OH one probably is functional, but there is no carboxylic acid in that reaction to react with that in order to form an ester. And I think they're pretty much the only three we've extensively done. I think in your homework, there is a list of polyvinyls, polyurea. I can't remember the full list down there. Actually, I've got it here. Yeah, polyvinyls, polyamides, polycarbonates, polyurethanes, polyureas, polyethers, polyanhydrides. So there is 1, 2, 3, 4, 5, 6, 7, 8. There is 8 different linkages that you can have there. So if you know what functional groups react to form those linkages, I can pretty much promise you won't see any more during this course.
Okay.
Okay.
Yeah, thank you.
Good, no problem.
I had a quick follow-up question about that.
Yeah.
So for J and K, it's the monomers and they have the potential to react with themselves. So are we just assuming that it's a random copolymer?
Oh, yeah, good question. So what do you need in between two of those monomers that you would link together?
Do we need like a squiggly line?
Exactly, you need a zigzag. Because that's a good question, because they could react with themselves or they could react with the other monomer in order to form a polymer. We don't know which order they would react. Presumably, if we were in a lab, we'd probably change the stoichiometry of that reaction, so we can change the different reagents, the different components and the mixtures and the concentrations of them. But unfortunately, we don't know that. So if we don't know that, we put a zigzag line in between.
Great, thank you so much.
Great. Every question I have, I think students answer the question well themselves. Confidence, that's what we need. Good.
Dr.
Any more? Yeah.
So when you're classifying the type of linkages for
Yeah.
polymers, do we only look at what I guess functional groups are in the backbone only, or can we also look at the pendant groups?
So you are really only you're only really looking at the backbone reactivity at the moment, right? Because we haven't gone into, we're just forming a polymer.
Mhm.
We haven't gone into the functionality of those side groups, which will be important when it comes to the applications.
Okay.
Right? So some of those side groups are hydrophilic for a reason, some are hydrophobic. Actually, what we talked about today with the LCSTs, I think, is polynipam. If you read about polynipam, that has an interesting temperature response, and that's to do with the fact that the group on the outside is both hydrophobic and hydrophilic, depending on what temperature it is. So that's when they become important, when we're looking at the properties and the applications of them.
Got it. Yeah, because I was seeing some examples where I guess they're polyvinyls. It's just a hydrocarbon backbone, but
Yep.
then the pendant groups will have like an ester or something like that. So I was wondering.
Oh yeah, of course, yeah. I mean that can happen, but the main thing is that when you're thinking about the polyvinyls, right, they can react and keep expanding it in to get bigger and bigger, because we can do the free radical polymerization. Free radical is the one that we deal with the most. But when you get to looking at the pendant side chains, right, there is actually, unless there is two of those on one molecule, you can't polymerize in that direction. If that makes sense.
Yes, it does. Thank you.
Okay. All good. It's gone quiet. We are all good.